Question 16 asks us first of all to explain why phosphorus and arsenic have very similar chemistry. Now you can't just say they're in the same group, although that's true, because it says to do it in terms of atomic structure. So you have to remember that if they're in the same group, what that actually means is they have the same number of electrons in their outer shell, and that is what you have to say for that first bit. Then it wants us to identify the sole stable isotope of phosphorus. So for that you need first of all to look up the relative atomic mass of phosphorus, and what you find is that Ar is 31.0, and you have to remember what that means. Relative atomic mass is the weighted mean mass of all of the stable isotopes. So if there is only one, and that's what it tells us in the question, then obviously the mean of one number is that number. So therefore the only isotope must be phosphorus 31. And you must be very careful to make sure that you write it like that. If you put the 31 somewhere else, like here or somewhere, all of these will get marked wrong. So it's very important that you know where the mass number goes, top left, the atomic number goes bottom left, and so on. If you put them in the wrong place, you're likely not to get the mark. Okay, part C asks us to write down the electron configuration for a P3- ion. Now when you're asked for ion configurations, I think the safe way to do that is to start by writing down what the atom would be, and then to amend it to take account of the electrons lost or gained. So just reading through your periodic table for phosphorus, we're past the first row, so we've got 1s2 in place. We're past the second row, so we've got 2s2, 2p6 in place, and we're into the third row. Past the s block on the left hand side, so we've got 3s2, and then in the p block it's the third one across, so it's 3p3. Now that would be a phosphorus atom, but remember we were asked for P3-. So remembering that an electron is a negatively charged thing, 3- means it has 3 extra negative charges, 3 extra electrons. So we just add 3 more into that 3p subshell, and that becomes 3p6, and that's your answer. Okay, with part D then we move on to ionization energies. First it wants the definition of the first ionization energy. So there are just a relatively small number of definitions like this that you really do need to learn, because if you try and put it in your own words you probably won't get it quite right. So the exam board version is that it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element. So just learn that, and that's easy marks then. Now it wants an explanation of this trend. So this is the successive ionization energies of phosphorus, and it wants to know why there is a big jump there between the 5th and the 6th. So remember, this is about the change of shell. Phosphorus is in group 5, so it has 5 electrons in its outer shell. So 1, 2, 3, 4, 5 relatively easy ionizations because they're the outer shell ones. And then the 6th one has to come from the next shell down, because you've already emptied the outer shell, and so that's much harder to remove. So that gets you 1 mark for explaining about that this comes from a lower shell. Don't just say different, say lower, or if you like specify. Remember, these are in the 3rd shell, so this one comes from the 2nd, but don't be too vague. To get the 2nd mark you need to explain why that should make such a big difference. So it's about the fact that because this is in a lower shell, the electrons are closer to the nucleus and also less shielded from it, because there are fewer inner shells doing that. So closer and less shielded, therefore these are much more strongly attracted to the nucleus. And that idea of nuclear attraction is always key in these ionization energy questions. Okay, and then finally on this little bit it wants us to draw the trend that we might expect for aluminium. So for this we need to be very clear where aluminium is in the periodic table relative to phosphorus, because that's going to have a big impact on this. So looking at that, what you see is that aluminium and phosphorus are both in the same period. Okay, they're both in period 3. The difference is that aluminium is in group 3, phosphorus is in group 5. So that has 2 important consequences. One is that because it's only in group 3, it only has 3 outer shell electrons, so that's going to mean you get a jump after 3 instead of after 5. But secondly, it means we've got to think about the trend across the period so that we can decide whether aluminium is going to come higher or lower. Okay, that's an important part of this question. So let's just review that. Remember, what happens as you go across a period is that most of the time the ionization energies increase because the increasing nuclear charge pulls the electrons inwards more strongly. So going from group 1 to group 2, you get an increase. 2 to 3 is one of those places where it bucks the trend. It dips back down because you change from removing an S electron to a P electron, but then it goes back up as we take electrons from the P subshell. When we get to group 6, it dips back down again, and that's because now we're having to take a paired P electron rather than an unpaired one, but then it carries relentlessly on upwards again. So that's what the overall trend looks like. As far as we're concerned, we're interested in this one, which is in group 3, and this one, which is in group 5. So you can see there's no question. Phosphorus is going to have a higher first ionization energy than aluminium. So that means when we draw aluminium, we start lower down. So we're going to have 3 relatively easy ones, and then because it's in group 3, that's it for the outer shell. So now there's going to come the jump. Okay, so it's going to look like that. Now the second shell, which is the next shell down, has 8 electrons in it. So if we count across, it's 1, 2, 3, 4, 5, 6, 7. No jumps within that because it's all in the same shell. Different subshells, but not different shells. And subshells don't really show up on this kind of scale. So we've taken 7 from the second shell. We haven't emptied it, so no more jumps. And that's the end. That gets you your marks. Part H, it wants a dot and cross diagram for arsine, ASH3. So this is a nice easy one. So we've got the arsenic in the middle, 3 hydrogens around it. And hydrogen can only ever make 1 shared pair because it's just got the 1s orbital to play with. So you know that's how the bonding's going to work. And then you just do the usual accounting and reckon arsenic's in group 5, which means 5 outer shell electrons. It's only used 3 of them, and therefore it has a lone pair as well. So that will be the dot and cross diagram. And then in the second part of that question, it wants us to relate that to the shape. So remember, this is about electron pair repulsion theory. You've got to learn all about this and make sure that your answer is couched in terms of that theory as well. So when you have 3 bonded pairs and 1 lone pair, remember it's the repulsion between those that dominates the shape. So we say we have 4 regions of electron density, and then specify what those are, because it makes a difference, obviously, whether they're lone pairs or bonded pairs. So 4 regions of electron density, specifically 3 bonded pairs plus 1 lone pair. And you have to make it clear that they're repelling each other. So you just write that down, repelling each other. And then ideally you explain what the location of these is, so in the outer shell of arsenic. So that's the origin of the shape, and then you've just got to remember what the shape is that follows from that. So it's like ammonia, which is obviously in the same group. NH3 and ASH3 are closely related, so that shape is called pyramidal. You need to remember that, these terms, and to draw it, it looks like a tetrahedron, but with one of the bonds replaced by a lone pair. So the easiest way to draw it is like that, with the 3 bonds pointing downwards from the tetrahedron, and then the lone pair at the top. It doesn't ask you for the bond angle in this shape, so don't give it if it doesn't ask for it in case you get it wrong. It would actually be 107 degrees, but it doesn't ask for that. So that would be enough to get you the marks. Part 3 asks us to account for the difference in volatility between these 2 compounds, and it tells us the numbers that relate to that at the top of the page. So volatility is how easily these things vaporize, and from the data at the top of the page you can see that arsine has a lower boiling point than ammonia. It gives you the data at the top of the page that tell you that, and that means that it's more volatile, because volatile means easy to turn into a vapour. Okay, so make sure you get this the right way round. So what you're looking for is an explanation for why it's easier to vaporise arsine. So these are simple molecular compounds. They have very similar structures because arsenic and nitrogen are both group 5 elements. So what we're talking about is why it's easier to break the intermolecular forces for ammonia than for arsine, because that's all you ever do when you vaporize a simple molecular compound. So don't talk about strength of covalent bonds, don't talk about ionization energies, it's all completely irrelevant. It's just about the intermolecular forces. And the key thing is that nitrogen is much more electronegative than arsenic, so much so that it's on that list of the magic elements which are able to withdraw electrons strongly enough from hydrogen that they can form hydrogen bonds. So remember, if hydrogen is bonded to any one of those three, nitrogen, oxygen or fluorine, then that hydrogen will be able to form hydrogen bonds. So that's true therefore for ammonia, but it's not true for arsine. And that's the key difference. So what you say is that ammonia can form hydrogen bonds, whereas arsine can't. Now you then need to say, well, what can arsine do? And you can see that it's going to be a polar molecule, because these are not going to have identical electronegativities. You normally expect hydrogen to be less electronegative, so you normally expect the hydrogen to be delta positive, but it doesn't really matter. You can see that there's going to be an electronegativity difference, and therefore it's going to be delta negative at the top, delta positive at the bottom, or possibly the other way around, but there's going to be some kind of dipole there, because it's one of those shapes with low symmetry. So we can say it will have permanent dipole-dipole forces, but the point is they're weaker. So ammonia can form hydrogen bonds, arsine can't, it can only form permanent dipole-dipole forces. They are less strong than hydrogen bonds, therefore it takes less energy to break them, and therefore it vaporizes more easily. That's the key point. So make it clear the difference. Don't just say ammonia can form hydrogen bonds, make it clear that arsine can't. Say what arsine can do, form permanent dipole-dipole forces, but then spell out that those are weaker than hydrogen bonds, so it takes less energy to break them, and that's why it's more volatile. You have to read the question carefully. It's easy to fall into the trap of just making a simple mistake like saying, oh, arsene's got more electrons, it'll form stronger induced dipole-dipole forces. And that's true, but that's the wrong way around then, because that would lead you to think that this would be harder to vaporize. And that doesn't fit with the data. So although it's true, it's outweighed by the hydrogen bonding. That's the big one that really makes the difference.